Hey everyone, so today we are going to see the solutions for the questions which are asked on the subject linear algebra in GATE 2024 examination for the program Data Science and Artificial Intelligence. So today we are only going to see the questions on linear algebra. So we will see the solution one by one. I will also be posting a link in the description from where you can actually download the question paper and see the question. I will be writing the questions over here, but still if somebody wants to see the question from the question paper, they can go to the link and download the question paper. So without wasting any time, let's go for the first question. So here is the question number 13, which is on linear algebra. So a 2 cross 2 matrix is given to you and the question is about the eigenvalues. Okay, whether the eigenvalues are complex, reals and all. You can see the question. So or otherwise let me show you the actual question. So here is the question. So it says that we have to choose which of the following is a true statement. So A, B, C, D, 4 options are there, whether the eigenvalues are non-negative real, complex conjugate pairs, positive and real, or non-negative and real, and so on. So yeah, let's see the solution. Now here, the first step is what we need to find the characteristic polynomial. So how do you find the characteristic polynomial? One is the standard way, you do determinant of m minus lambda I equal to 0. So you do m minus lambda I, then take the determinant, you get the characteristic equation. What is other way? Other way is lambda square minus trace of the matrix. What is trace? Sum of the diagonal entries, which is 2 plus 1, 3, 3 lambda plus determinant of m. What is determinant? 2 into 1 minus 3 into minus 1. So it's nothing but 5 equal to 0. So using this, you can directly get the characteristic polynomial. Instead of going this traditional way, in competitive exams, we should know all these tricks. And now I think it's easy, right? You have studied the formula in your 7th or 8th in the factorization. So the formula is what? When you have ax square plus bx plus c, the formula is minus b plus minus square root of b square minus 4ac upon 2. Now no need to go further. Directly you can see this discriminant part, the term inside the square root is negative. That means complex number will come into the picture. As soon as you have the complex number, we know that for the polynomial with real coefficients, complex roots always occur in pair. That means if one complex number is a root, then its conjugate is also the root. So here itself, like in 2 lines, you can immediately say that B option is the correct option. That is the eigenvalues. They are in conjugate pairs. So I hope this is clear. If you have any doubt, you can ask me in the comment section. Otherwise, let's go for the next question. So next question is question number 35. So in this question, the matrix is given to you and the question is you have to tell the determinant of m square plus 12m. Now one standard way is you find m square, then you do 12m, you add up, you get a new matrix, then find the determinant, you get the answer. But obviously that's a very tedious way to solve, so you have to not go by that way. The first step you do is you first take out m common from here. So it is m into m plus 12 times the identity matrix. That's the first step. Second step, what is determinant of the product? It is nothing but the product of the determinant. So determinant gets split with the product. So now I want to find determinant of m and determinant of m plus 12i and then multiply. So from here, yeah, things are good because you don't need to do m square. So that is first step. Okay, first simplification. Now here also, you can find the determinant, as one thing, but if you observe m carefully, you can observe your third row is nothing but the addition of first 2 rows. 1 plus 3 is 4, 2 plus 1 is 3, 3 plus 3 is 6. That means what? Your third row is the addition of first 2 rows. So that means it's a linear combination. That means what? Whenever you have this combination thing, or one column or one row is depending on other rows, or they can be obtained from other columns or other rows, then the determinant of such matrix is always 0 because the rank is less than 3. In this case, rank is less than 3 because all the rows are not linearly independent. Okay, so if you know the language of linearly independent, then the answer is my third row is a linear combination of first 2 rows, therefore the determinant is 0. And if you don't know the concept of linear independence or dependence, no problem. Just try to see some kind of combination is there or not. Whether one row or one column can be obtained from other rows or other column. If that is the case, then determinant is always 0. Okay. So because of that observation, I know determinant of m is 0. Whatever this be, I don't care. The product is always 0. So with this property, taking out the common and property of determinant, one has to simply find determinant of m, which is 0. So no need to find this value. Your final answer is 0. So again, if you know this trick, I think it should not take more than 15 to 20 seconds. Okay, so I hope this is clear. Let's go for the next one. So question number 47 says you have to select the sets which are the subspaces of R3. Okay, so let's go one by one. So let's try to see the first option. So what is the first option? All those vectors which is alpha times the one vector plus beta times the one vector. Now keep this in mind. This is nothing but the span, SPAN, span of which these two vectors. What are these two vectors? 1, 0 and 1, 0, 0. Because what is span? Span is nothing but you take all possible linear combination. And that's what we are doing. My alpha and beta are real numbers. So we are taking all possible linear combinations. So span of any set is always a subspace. If you don't know the concept of span, it's okay. Just keep this thing in mind. Whenever you take the linear combination of two vectors, where your alpha and beta can be any real number, there is no restriction. As soon as the restrictions come, it is not a subspace. So whenever there is no restrictions on alpha beta and you are taking the linear combination, then it always forms a subspace. Now one can prove that, but proving will take a lot of time, but I will just give you the idea. So if you take two vectors, say x bar and y bar from the set. So what is your x bar? It is some alpha 1 times this vector 1, 1, 0 plus beta 1 times another vector 1, 0, 0. How your y bar will look like? It is alpha 2, some scalar, because this can be any real number, but these two vectors are fixed, plus beta 2 times 1, 0, 0. Now when you add up these two vectors, what do you get? You get alpha 1 plus alpha 2 into this vector plus beta 1 into beta 2 plus this vector. Okay, so what you are having? You are having alpha 1 plus alpha 2 into the first vector plus beta 1 plus beta 2 into the second vector. But this is some real number, let me call it alpha 3. This is some real number, let me call it beta 3. So addition is again the combination of the given two vector. So if I am taking two vectors from the set, their addition again falls into the same set. What about multiplication? If I take some c times x bar, so it is c times this plus c times this. But c into alpha 1 is again a real number, c into beta 1 is again some real number, therefore it satisfies scalar multiplicity as well. Therefore the given set is a subspace. What about the second one? The second one, if you see, there is a restriction, there is a condition on the coefficient. What is the condition? Here alpha square and beta square are mentioned. Alpha beta can be any real number, but problem is here alpha square and beta square is coming, and because of that you will never have a negative vector over here. Like this will never be negative, this will never be negative. Even though alpha and beta will be negative, when you square it will never be negative. So therefore this is positive, this is positive, this is positive, this is positive, so everything is positive. So here scalar multiplication will create a problem, because what the scalar multiplication says, my c times x bar should also belongs to a set for a set to be a subspace. If I take c to be minus 1, then minus 1 into x bar will be a negative vector. But what is the set given to you? In the B option, set consists of all the entries are positive. So if I multiply by a negative number, then the answer will I get is a vector with the negative components. Therefore, the scalar multiplicity fails and B option is not the correct answer. Let's go for the C part. Now C part is again good. What we are having? We are having a condition. So these are the two conditions given to us. Okay, so 5x1 plus 2x3 equal to 0 and 4x1 minus 2x2 plus 3x3 equal to 0. Now I have done one lecture on tricks to determine the subspaces. I will post the link in the description. If you have seen that lecture, within a fraction of a second you can say, oh, this is a subspace. So the trick is, whenever the variable has degree 1 and there is no product of the variables, so yes, all the variables are having degree 1, there is no product of the variables and there is no constant like plus 4 or equal to 7, equal to 6, there are no non-zero constants. Whenever you have such a thing, then that set is always a subspace. Okay, so this forms a subspace. If someone wants to prove, it will take some time to prove, but I will give you the hint. Okay, so what is the hint? You take x bar to be x1, x2, x3 and you take y bar to be y1, y2 and y3. These two vectors are in the given set. That means what? These components, they satisfies both the equation. What you want to prove? My x bar plus y bar is in the given set. That means I want to show that x1 plus x1 plus y1, x2 plus y2 and x3 plus y3 satisfies the given conditions or the given equations. So when you replace here x1 plus y1 and here x3 plus y3, you take them inside and use this case that this vector satisfies this equation, this vector satisfies this equation, and you get equal to 0. So that's the hint. But yeah, just keep this in mind. Whenever the degree is 1 and there are no product terms, your answer is always, and there are no non-zero constants, it always forms a subspace. So see that link in the description for more idea, and if you still have any doubt in this, you can ask me in the comment section. And with the help of this trick, now you can see the D part. In the D part, you can see there is a non-zero constant. It says all those vectors of the form 5x1 plus 2x3 plus 4 equal to 0. Now you are having a non-zero constant. So this set will not form a subspace. If I want to give you a specific reason, you can see that 0 vector does not satisfy the equation. If I take 0, 0, 0, so if I put 0 here, is 0, 0 satisfying this condition? No, I am getting 0 plus 0, 4. So 4 is not equal to 0. So this set doesn't contain the 0 vector, therefore it is not a subspace. Okay, so the correct option for this is option number A and option number C. So I hope this is clear. If you have a doubt in this part, you can ask me in the comment section. Next question is question number 48, and it deals with the solution for the system of linear equations. Okay, so for this one should know the concept of rank. You can again, I will post the link in the description. You can see that lecture on the rank topic where I have given the solution, but for the sake of completeness, let me give the solution here as well. So what does the theorem says? Theorem says if you find the rank of A, rank of this matrix, which is maximum number of linearly independent row vectors or the column vectors, if the rank of A is not equal to, or you can say if it is less than rank of A augmented B, that means the system has no solution. Okay, if rank of A is equal to rank of A augmented B is equal to number of columns for the given matrix, then the system has a unique solution. And if the rank of A is equal to augmented is less than n, then the system has infinitely many solutions. So these are the things that we are going to use. So if you see the first option, it says there exists a matrix M, P and Q such that MXP has a unique solution and MXQ has an infinite many solution. Now when I am saying MX equal to P, it is having a unique solution. That means what? My rank of M is equal to rank of M augmented P is equal to number of columns. And number of columns are 3. It's a 3 cross 3 matrix. So this says that the first thing says Mx equal to P implies my rank of M is 3. And what does the second says? Mx equal to Q has infinite solution. That means rank of M equal to rank of M augmented Q is less than 3. So first condition says rank of M should be 3. Second condition says rank of M should be less than 3. Can you have a matrix whose rank is 3 as well as whose rank is less than 3? Answer is no. Rank for a given matrix is always unique. Okay, so you cannot have a matrix with two different ranks. Therefore, first answer is false. There does not exist matrix M and the vector PQ satisfying both the condition. Okay, so A option is false. What does B option says? It says there exists a matrix M, vectors P and Q such that Mx equal to P has no solution. Mx equal to P has no solutions means what? Rank of M is less than rank of M augmented P. And the second says Mx equal to Q has infinitely many solution. Means rank of M equal to rank of M augmented P is, Q is less than 3. Okay, so yeah, this case is possible because what you can do is you choose M to be of rank 2. So if I take rank of M to be 2 and Q also such that this is rank of M is 2 and rank of M augmented Q to be 2. then rank of m and rank of m augmented q is same, but it is less than number of columns. So this condition is satisfies. And now you choose your p such that rank of m augmented p is 3. So that means this condition is also satisfied. 2 is less than 3, and this is also satisfied. 2 equal to 2 less than 3. So you can always choose m, q and p which satisfies this condition. Okay, now what can be? You can always choose this matrix which satisfies this condition and your job is done. So therefore, yes, there exists such matrices satisfying both the condition. So B option is the correct answer. Let's go for the next one. Mx equal to p has a unique solution. Is that possible? If I am saying that mx equal to p has a unique solution, means what? My rank of m should be same as rank of m augmented p should be same as number of columns. But number of columns are 3. Okay, so rank of m equal to rank of m augmented p. What it is saying? It is saying that it has a unique solution. But is this possible? No, because my m is a 2 cross 3 matrix, 2 rows 3 column. So rank of any matrix is at most minimum of rows comma column. So minimum is nothing but 2. So rank of m can be max to max 2. So therefore this condition is not satisfied. So what I am saying is, since your m is a matrix of order 2 by 3, the maximum rank your m can have is 2, because there is a result which says that rank of a matrix is at most minimum of number of rows comma number of columns. And the first condition says that mx equal to p has a unique solution. When does a system has a unique solution? When the rank of a matrix is same as rank of m augmented p is same as the number of columns, which is 3. Whereas rank of m can never be 3, it can be at the most 2. Therefore C option is also wrong. And last we are left with the D option, which is again a correct option. Why it is a correct option? Because it says that mx equal to p has a unique solution. That means rank of m equal to rank of m augmented p is equal to number of columns. There are 3 columns, sorry, there are 2 columns. And the second condition says that your mx equal to q has no solution. Means rank of m is less than rank of m augmented q. Yes, that is possible. You choose your m and p, you choose a rank m of rank 2, you choose a p such that rank of m augmented p is also 2. So this condition is satisfied. Now rank of m is 2, right? So you choose q such that rank of m augmented q is 3 and your job is done. Okay, so this scenario is also possible. Therefore the correct options are B and D. If you want any more clarification on this question, you can ask me in the comment section. Now what does question 49 says? It says that if R is a set of real numbers, U is a subspace of R3 and M is a 3 by 3 matrix and corresponding to the projection on the subspace U. That means what? Your M is a matrix from R3 to U is a projection map. That means what is image of M? Image of M is U. That means what can you say about the rank of M? It is nothing but, what is my U? U is a subspace of R3. So it is nothing but the dimension of U. Because it is projection, image is the complete thing. So whatever the dimension of U is, that is nothing but the dimension of image. Dimension of image is nothing but the rank of M. Okay, so this is given to me. Now let's go for the first one. It says that U is a one-dimensional subspace of R3. Then the null space is one dimensional. So if dimension of U is 1, that means what? Rank of M is 1. What is your rank nullity theorem? It says that rank of a matrix plus nullity of the matrix is nothing but the number of columns or the dimension of the domain, which is 3 in this case because we are in R3. So rank is 1. If they are saying if the dimension of U is 1, that means the rank is 1, then the rank nullity theorem says your nullity has to be 2. Whereas they are saying that M a null space is one dimensional, which is wrong because the rank nullity theorem says your null space has to be 2 dimensional if U is 1 dimensional. Okay, because if U is 1 dimensional, then rank is M. As soon as rank is M, rank nullity theorem says the nullity has to be 2. Nullity is nothing but the dimension of the null space. So the first option is incorrect. What about the second? They are saying if your U is 2 dimensional, then what does the rank nullity theorem says? The null space is 1 dimensional. What they are saying, Yes, null space is one dimensional. So B option is correct. What about the third? Well, there is a nice result. Is what are the projection matrices? If you have studied linear algebra in detail, a matrix P is said to be a projection matrix if when you square you get the same matrix. Now your M is a projection matrix, therefore your M square is M. Therefore the third option is also true. Now you multiply both side by M. What do you get? M cube equal to M square. But what is your M square? Your M square is M. So your M cube is also M. So for this question, the correct answers are B, C and D. And here is the last question. What does it say? It says that a vector u is given to you, which is nothing but 1, 2, 3, 4, 5. They are asking you the sum of the singular values. Now, what are the singular values? For that, you first need to find u into u transpose. What is u into u transpose? It is nothing but here 1, 2, 3, 4, 5 and here 1, 2, 3, 4, 5. So your matrix will be a 5 cross 5 matrix. 1 into 1 plus 2 into 1, 3, 4, 5. Then 2 into 1, 2 into 2, 2 into 3, 2 into 4, 2 into 5. Then again 3 into 1, 3 into 2, 4 into 1, 5 into 1. You have a 5 cross 5 matrix. Now the next step is you need to find the SVD decomposition. That means you have to write this as U sigma V transpose, where my U and V are orthogonal matrices and U sigma is a diagonal matrix with diagonal entries as singular values. Now this is a too much thing to do. Obviously in competitive exams you don't get such big questions. So obviously there has to be some trick involved in this. Now there is a very nice result which says that if your matrix A is symmetric and positive semi-definite, then the sum of the singular values is equal to the trace of the matrix. So in this case, if this is my M, what are the sum of the singular values? No need to find this sigma. The sum of this, if this matrix is symmetric and positive semi-definite, then the sum of the singular values is nothing but you take the trace of the matrix, which is 1 plus 4 plus 9 plus 16 plus 25, and that's what the answer is. Provided your M is positive and symmetric and positive semi-definite. Is it symmetric? Yes, because what is my M transpose? It is U transpose ka transpose. But what is this? U transpose into U transpose, which is U into U transpose, which is M. So my M is a symmetric matrix. Is it positive semi-definite matrix? Yes. When do you say a matrix is positive semi-definite? When all the eigenvalues are greater or equal 0. But okay, no need to find the eigenvalues. When do you say a matrix A is positive semi-definite? If X transpose AX is always greater or equal 0. Now is this greater or equal 0? Yes. Why? Because this is nothing but U bar into X bar transpose into U bar transpose into X bar. Let me call this as Y bar. So Y bar transpose into Y bar. What is Y bar into Y bar transpose? This is nothing but mod of Y square. You can check it out. Okay, you can take any vector. Say Y bar is 10, 20, 30. So what is Y bar transpose? 10, 20, 30. What is Y bar? 10, 20, 30. You multiply, you get 10 square plus 20 square plus 30 square, which is nothing but the length of this vector, square of the length of this vector. And this is always greater or equal 0. Therefore, this is your positive semi-definite matrix. So this U into U transpose is symmetric and it is positive semi-definite. Therefore, the sum of the singular values is nothing but the trace of this matrix. And trace of this matrix is nothing but 1 plus 4 plus 9 plus 16 plus 25. And that's what the answer is. So I hope all the solutions are clear to you. If you have any doubt, you can ask me in the comment section. Thank you.